Welcome to Mastering Solutions. This question is really important to draw a picture so we can visualize what's going on. They tell us that we have a CPU here. So we have CPU, and it's sending information out to different parts of the computer, and then that information comes back, right? So they tell us that over here we have a memory unit, okay? And it says that the information gets sent out from the CPU. That information gets processed over here by the memory unit, and then it sends it back over here. They tell us that the processing time is a half of a nanosecond, so 0.5 times 10 to the negative 9 seconds. And they tell us that the total time to go here, process, and comes back takes 2 nanoseconds. So total is 2 10 negative 9 seconds. And then from that information, we have to figure out how far away can the memory unit be from the CPU to process in time. They also tell us in the information that the index of refraction of the silicon fibers that they're using is 3.50, and we'll see why here in a moment. First off, we need to figure out how much time we have available for just the traveling, right? So we have 2 nanoseconds minus a half of a nanosecond. So the total processing time, or excuse me, not processing time, the travel time is 1.5 nanoseconds that we have available. Now we're going to use the velocity equation, and that's just like we remember from way back. It's velocity equals the change in the distance over the change in time. Now we need to change it just a little bit because the distance that we're traveling here is 2, because we have 1 of the distance to go out to the memory unit and then the exact same distance to come back. So let's put that as velocity is equal to 2 times x over the change in time. And now we're trying to solve for the distance here. So we need to isolate the change in the distance. So let's first multiply both sides of the equation by delta t. Okay, let's give us a little bit more space. So now we have the velocity times the change in time is equal to 2 times the change in distance. And I'm going to put 2 times x just because I don't want you to get confused thinking about, well, the total distance is delta x. So we're just going to say 2 times x, and one of these is what we're saying is x. Okay, so now let's divide both sides of the equation by 2. Divided by 2. So our equation that we'll be using is the distance x is equal to the velocity times the change in time divided by 2. Now, what are we going to use for the velocity? Because we're talking about light here. So you can remember that the formula for velocity for light is v is equal to the speed of light in a vacuum, c over n. So this is where the 3.5 from the index of refraction comes in. So now we can just plug that straight in for v. So our final equation that we'll be using is x is equal to the velocity, which you said is c over n, times the change in time, all divided by 2. And we have this solved for just 1x because that is the maximum distance that it can be set, because we're going 2 times this for the full travel of the light. And so that's where the divided by 2 comes in. So if we plug in our information, we have x is equal to c, which is 3 times 10 to the 8th meters per second, divided by n, and that's 3.50. And remember, index of refraction doesn't have any units. We're going to multiply that by the change in time. And the time that we had available, we said, was 1.5 nanoseconds. All of that will get divided by 2. And now some of you might get confused by this. You can also write it another way, and it's the same thing. We can also say c times delta t divided by 2n. These are equivalent. So when we come to our calculator, I'm going to plug it in the first way. So we'll have 3 times 10 to the 8th divided by the index of refraction, which we said was 3.5. And then that gets multiplied by the time available, and that's 1.5 times 10 to the negative 9. And then all of that gets divided by 2. So our answer for the maximum distance that it can be is, this is in meters, so we have 1, 2, so 6.4. So our answer for how far away the memory unit can be, the maximum distance, is 6.4 centimeters. And that's the maximum distance for the given time available that was in the problem, the 1.5 nanoseconds for the travel time.